Andrew, can you hear me? Okay. Gord, I'm signed in as me, and I don't see any place where I can allow somebody to be co-host.
It's just me that has control over that. So Sophia joins.
So somebody's going to have to make Sophia.
Yeah, I'll do that when she signs in. Can you hear me?
Also, well, I can try signing in as host again. But I think that just makes me co-host.
No, that's fine. Don't do anything. Can you hear me, Alan?
Can anybody hear me? Because I can't hear anything.
I hear you, Lee.
Oh, good, thanks. Now I know my ears are working. Thanks.
Good. So I now have audio too. Very happy.
Yeah, okay. Sorry, the moment there, I thought my sound was not working, so good. I'll shut up now.
So do you have the presentation up?
I see it looks like the opening page up on here. Yeah,
Perfect. Thank you.
yep.
And it's all on YouTube now.
Yeah, I got that warning too as I signed on.
Yep, I'm watching it on YouTube as we speak.
Oh, great. I'll turn on my camera. Here we go.
I think it wants you to select the background there, Alan. You're up on the main page there, but not in your little window.
Confusing.
It'll be up at the top of the screen this time because you're sharing.
Oh, yeah. Yeah, I got it. I'm shy. Camera shy. So on our YouTube, we should see it. Oh, live, it says.
I presume that our YouTube channel, that people will be, it's recording, so people will be able to see it even if they miss the meeting.
Yes.
Is that YouTube channel on our webpage, like where anybody can find, not just for this meeting, but anytime we put stuff on there?
I don't know if there's a permanent link to our YouTube channel on our webpage.
Yes, there is. Oh, actually, I'm not sure. There is on now. Home.
Like we must have more recordings
Do.
that are on our channel that maybe people don't know about.
Yeah, there's a number of recordings there. Not as many as there should be because I've run behind on actually editing and posting these things, but there are a number of videos up there.
Maybe after the meeting, I'll look on the webpage and see if there's a way to get onto the YouTube like selection to see what's there and that. And if not, maybe we can get that sorted out.
Oh, we're getting near showtime. I noticed that the link didn't give the passcode, but I guess you can just click on the link and you're in.
For the YouTube stream?
No, on our member invite.
Oh, if it's a big, long URL with a bunch of funny looking characters in it, then you don't need a password.
Good.
Yeah, I just had to copy and paste it into my browser and it opened up right away.
Hi, Sophia.
Hello.
All right, good. We've got you there. Perfect.
Yes.
So Gordon, can you make Sophia a co-presenter so I can stop sharing screen and she can at some point?
Already done.
Thank you.
I would say hi to everyone, but then I don't think anybody here knows me. I was a life member about, well, I'm still a life member, but I joined in 74, so it's been a bit.
Wow.
I'm glad I caught wind of this show. It's going to be very interesting.
Well, you must have known Paul Sykes.
Yes, I did. As a matter of fact, several years before he passed away, what was that, about maybe 80 or something? I can't remember exactly, but yeah, I left the area in 81 to go to Calgary. Managed to work my way up the ranks for a little while there, but then the minus 30 degrees is not exactly observing weather for a wet coast type person, so I came on back.
Oh, okay. Welcome back.
But with my time allotments, I think this Zoom is about the only things I can really readily attend. Anyway, I'll step out of your way. It's almost showtime.
Just about. Okay, I make it 7:30. Of course, my slideshow's stuck now. I'm not sure why.
Technology.
It's bound to get me. Why? Zoom's fine.
We have control of your set.
It seems that way. Oh,
We have the horizontal, we have the vertical.
apparently.
Saw your mouse. Oh, there's your mouse. There you go.
Okay, we're away. Well, that's good because as people drift in, I can give our little president's introduction. My name's Alan Jones. I'm president of the Rask Vancouver Center. Welcome everyone tonight. First, who we are. We are Rask Vancouver. We're 90 years young amateur astronomy club. We're a registered education charity. We're associated with Canada's oldest society, the Royal Astronomical Society of Canada. And our center has 300 members of over 5,000 in Canada. Our primary objective is to stimulate interest, promote and increase knowledge in astronomy and applied sciences. And our second and many other objectives is to further progress of astronomy in Canada. You see the shots around the slide. This shows how much we are involved in community in the community and public outreach. Whoops, didn't mean to go there. Let's see if I can arrow back. Our website is raskvancouver.com. You're welcome to learn, support, join, share your knowledge. We welcome volunteers, and we do have a way to donate. Donations are welcome. Just gonna make a mention of some upcoming events. Starry Nights, we help host the Starry Nights program at Simon Fraser University. They were virtual, and now we've had 3 in person. They are every Friday night, weather permitting. Watch the Vancouver Astronomy Meetup for details. Our next monthly meeting is April 14th. Ruzbet Bidashari is one of our center members. He's a mechanical engineer with a lifelong passion for astrophotography, and he'll share with us many aspects of how he got started and go through some of the equipment he uses. One of his astro photos is on the cover of the, actually I said February, it's the March-April Sky News. And it was taken from an urban sky using narrowband filters. That's quite impressive. You'll see it on one of my last slides. And just a moment to explain what this memorial lecture is about and why. Paul Sykes was born in 1918 and died in 2005. He was born in Pennsylvania, United States, and picked up an interest in astronomy early in life. In his teens, he published his own monthly astronomical column. He was a decorated captain in the U.S. Air Force in the Pacific War during World War II. He was awarded a Presidential Unit Citation, the U.S. Air Medal, Oak Leaf, which indicates having won or been awarded a medal more than once, and the Bronze Star. He later earned a degree in physics in 1948 from University of British Columbia. We call it UBC here. He rejoined the US Air Force and attended the Oak Ridge School of Reactor Technology, studying physics. And he was part of a program which was working on nuclear rocket development. And through that effort, he achieved a rank of major. Paul returned to UBC as a lecturer and administrator in physics, and he retired in 1983. And one of our audience members tonight knew Paul. Paul passed away in October 2005 at the age of 87 and left our center a generous gift. So we have annual Paul Sykes Memorial Lectures. He was a lifetime Rask member. Our national publishes many publications to help people get started and continue in astronomy. Also teaching guides. We have observing certificate programs. So various levels of object lists. And we always invite you to join us. Our membership director is Marla Daskis. Her contacts here, as well as it's on our webpage. Members receive the Sky News. This is incidentally Ruse's photograph on the cover. You also receive the Observer's Handbook. This is last year's. It's 300 pages, or 350 pages. It's kind of the Farmer's Almanac of astronomy. We have a telescope loaner program, and we have an extensive library and use of the Trache Observatory at Simon Fraser University. And with that, I would like to turn it over to Andrew, who will introduce our speaker tonight. Andrew is our speaker chair, and I've got some. Are you unmuted?
Thanks, Alan. Everyone can hear me, right?
Yes.
Excellent. So yeah, I'm pleased to introduce 2022's Paul Sykes Memorial Lecturer, Sophia Gad-Nasr. She is a PhD student at the University of California, Irvine, looking into the mysteries of dark matter cosmology, as well as astroparticle theory. She's a professional science advisor and communicator with a ginormous, that's a scientific term, social media following who watch and listen to her explain her topics of research, as well as her love for hamsters, which I have on good authority that we will see. We're lucky enough that we've got access to her mind, her work, and her wit for the next hour or two. So for the comfort of your bedrooms, your home offices, your cell phones, or your lofts, I'll pass over to Sophia and she can take it away.
Thank you very much for having me. I'm really excited to talk about the universe today. And so, all righty. Can you all see my screen?
Yep.
Great. So today I'm going to tell you about how we can create black holes with dark matter at cosmic dawn, which is a very, very early point in the universe's history. Now, typically when we think about the cosmos, we think about the really bright things like stars, galaxies, and nebulae. These are the things that we typically will think about because that's what we really see. The thing is, there's more to the cosmos than meets the eye. In fact, galaxies are riddled with black holes all over the place, which we can't see because light can't even escape them. And they absorb light. Every big, large galaxy, including our own, has a supermassive black hole at its center, which we don't know how they formed and how they got there. In fact, the entire universe, all of it, every piece of the universe is covered in matter that we can't see. So it's not just the galaxies. There's actually this stuff called dark matter, and it's even in your room right now, passing through you at every given moment. So there's dark matter and then there's black holes. So is there a connection between the two, in particular supermassive black holes? I'm going to show you how there might be, and how, if this is correct, if this is how things work, then I'll be able to help answer two of the most imperative questions in cosmology. One being, of course, what is dark matter? And the other, how do supermassive black holes form? So let's talk a little bit about what black holes are. So black holes are things that happen when you take matter and you cram it into a really tiny space. You cram too much matter into a very tiny space. And then what happens, because matter interacts with gravity, is that gravity starts to act, and it begins to act sort of on it, causing it to collapse infinitely. And so because this happens, what you end up with is this black hole, which is an incredibly dense point in space where the singularity in the center is called infinitely dense because it kind of takes up like zero volume, but it has mass. And so And these things are so massive that they warp space-time so much that nothing can escape, not even light. The moment that you get too close, you're gone. And that's a point that we call the event horizon or the Schwarzschild radius. So I have someone on Twitter mentioned the possibility or asked me to calculate the Schwarzschild radius of my hamsters. And so this slide next here is where I do exactly that. And that's the reason why I had the equation up there at all, is because I want to calculate the Schwarzschild radius of my hamsters. Oop, don't know what happened there. Oh, great. Cool. So up here we have Charmini. She's named after the charm quark, which we'll learn about in a few slides ahead. And this is Muini, who is named after the muon. When I calculate their Schwarzschild radius, so if I was to cram enough of a Charmini or a Muini into a really tiny space to make it turn into a black hole, the Schwarzschild radius that we get is essentially 10 to the minus 29 meters. That's really, really tiny. In fact, a human being, which is about 2,000 to 2,500 times the mass of one of my hamsters, would give us something about like 10 to the minus 25 meters. So let's try something a little bit more, I guess, sensible, like maybe say the Earth. Now for the Earth, which is about 10 to the 24 kilograms, where the 24 just tells us that there are literally 24 zeros following this number in front. This gives us a 0.088 meter black hole. Oh, excuse me, Schwarzschild radius. Doing it for the sun, we find that the Schwarzschild radius is more like about 2.5 kilometers. Now, there's one black hole that some of you may have heard of, and if you haven't, it is the most massive black hole that we have ever observed. And it's called TON 618. I'm not sure exactly why, but it is 66 billion times the mass of the sun. So with this one, if we calculate its Schwarzschild radius, it's 10 to the 14 meters, which is about 12, almost 1,300 times the Earth-Sun distance. So what we call the Earth-Sun distance is an astronomical unit. And just for comparison, Pluto is about 40 astronomical units away from the sun. And then on the smaller end, an atomic nucleus is 10 to the minus 15. It has a radius of 10 to the minus 15 meters. So this is an extremely tiny Schwarzschild radius. And so, yeah. Now let's talk about the different kinds of black holes that we can get. So for example, there are some that are stellar mass black holes. Now these are black holes that form from the death of extremely massive stars. When a star dies, that is really massive, after it's basically fused all of its elements and it's kind of reached up to iron, you can't make anything after beyond iron and actually create energy. You end up losing energy to do that. So at that point, a star will collapse. And that collapse is never ending, leading to a black hole. And these ones exist throughout all galaxies, anywhere basically stars would be. But the most massive that you can get from a star would be something that's less than 100 times the mass of the sun. Intermediate mass black holes are an interesting point of conversation, because at some point we were wondering where these things were. We couldn't find them. LIGO found one that is, I think, about 160 times the mass of the sun, something that cannot be created, of course, by the death of a star. And so these are created by mergers, so essentially black holes that merge together, stellar mass black holes that merge together to create some bigger black holes. And they would be throughout galaxies as well, but quite more rare than stellar mass black holes, and maybe even in the center of smaller galaxies. And I'll show you how that can be true. And these black holes would be 100 to about 100,000 times the mass of the sun. Now these ones, supermassive black holes, they sit at the center of every single galaxy, including our own. Our own is 4 million times the mass of the sun. And we have no idea how they got there. We don't know how they formed. We have, I guess we have sort of ideas on how that happened, but we just, none of our current methods that we can explain how these things formed. And so I'm going to tell you how it might be possible that we can get supermassive black holes. And these ones are millions to billions of times the mass of the sun. What's inside a black hole? Some people think it might be that black holes are kind of like wormholes, so passages through space-time, shortcuts through space-time. Are they that? Do they hold entire other universes, or are they passages to entire other universes? Or are they tesseracts, sort of 5-dimensional spaces that transcend time so that you can go to any point in time that you wish, like Coop did, to get this information out to his daughter to let her know what she needs to do to complete the gravity equation? That's something we don't know, but what I can tell you is that if you were to enter into a black hole, the one that you would never want to enter is a stellar mass black hole. As we saw when when I was calculating the Schwarzschild radii, the smaller, or the less massive something is, the smaller the Schwarzschild radius. And so that means that the singularity, which is something that's at a point that's inside, in the center of a black hole, for a stellar mass black hole, that's going to be very close. And so what happens if you fall into a stellar mass black hole, because these forces, the gravitational force is going to be so strong, and it'll just pull you apart, and it's called spaghettification. And so when you go in feet first, your legs are going to get really long and stuff like that, and you'll probably die well before that, so you won't feel it. But the whole point is that we want to try to survive, and so the best way to do that is to go into a supermassive black hole, so that you can, like Coop, perhaps find out what is in there. At least safe, you'll be safe for a while, because the Schwarzschild radius, or the event horizon, is much further away from the singularity, which is something you don't want to reach. Now, another question then, since we're talking about formation and all these things, do black holes die? Yeah. It turns out that they do, and it's in this process called Hawking radiation, which was proposed by Stephen Hawking himself. And it's a quantum mechanical phenomenon. So in space, there are these little quantum fluctuations that happen. And when they happen, particles can come into and out of existence, where particles are the most fundamental building blocks of anything that you have. So the most fundamental building blocks of your chapstick, when you break this apart into its most constituent parts, you get these little subatomic particles. And so in these quantum fluctuations, particle and antiparticle pairs can form. If they form near the event horizon of a black hole, what then can happen is that the black hole can absorb the negative energy, the one with negative energy, and these particles would essentially pop in and out of existence, so they're called virtual, until this happens. So when they come near a black hole, if you're too close to the event horizon, you're no longer virtual if the black hole has absorbed the negative energy. And the negative energy is kind of like decreasing the mass that it has, whereas it releases the positive energy in the form of Hawking radiation. And so eventually, black holes will evaporate away. This is a process that has not yet been observed, but we are definitely looking for it. So, okay, interesting that we know how black holes might die, but how are supermassive black holes formed? We still don't know this. So it's not so much the problem of having supermassive black holes today, because black holes will eat things, so they'll accrete. It's called accretion. When you accrete stuff, black holes are eating things, pulling matter into them, as well as merge. And so over the course of maybe 13.8 billion years, you can get something quite massive. The problem is that we find them when the universe is just 700 million years old. Black holes that are the mass of 1 billion suns. And there's just not enough time for any of our conventional methods to be able to form something like this within that time period. So in the early universe, things could accrete really, really fast and really efficiently, and that's called super Eddington accretion. If this process were to proceed perfectly and just continuously, so it has stuff to accrete and to eat up continuously in the early universe, we can still, if we start with a stellar mass black hole, say on the upper end of the spectrum, say 100 solar masses, it can only create about 100 million times the mass of the sun. A black hole that's that massive, which is not enough to explain the black holes that we actually see there. So what we need are seeds that are more massive than just stellar mass black holes. And the answer may not lie in the things that we can see, like stars. It may actually lie in things that we can't see. So the universe is full of stars and things like that, but on the grand scheme of things, everything is covered in, and everything is shrouded in this stuff called dark matter. Now, dark matter acts like the glue that holds galaxies together and is really the reason why our universe looks the way it does today in this interesting looking cosmic web. And we know that it exists thanks to several observational pieces of evidence. One of them, which is, I guess, the most commonly talked about, is rotation curves. Rotation curves are when we measure the velocities, the speeds of stars in a galaxy from the center and moving outward, and we plot them, what we expect to see is something that we have tested in our own cosmic neighborhood, like our solar system. We have a giant laboratory where we could test gravity, and we've done it. And so when you look at the planets and the way that they move, the most massive part of the solar system is the sun. And so that's our sort of central gravitational potential where everything orbits around. And what we find is that the further away that you move from the sun, the slower your speeds are, because the force of gravity decreases by the square of the distance. And so Mercury is moving faster than Venus, Venus moves faster than Earth, and Earth moves faster than Jupiter, and Jupiter than Pluto, and so on and so forth. It's about the distance from the sun, as you can see, because Earth is still moving faster than Jupiter, and Jupiter is it's the most massive planet in our solar system, but it's about the distance, because relative to the sun, it's not, it's nothing. And so when we plot in a galaxy, in a disk galaxy, at least like ours, like the Milky Way and like Andromeda, we have it's kind of similar in that stars will orbit relatively on this sort of plane. And so we can plot the stars out, and we expect to see what we would see in our solar system, which would be essentially a curve that looks like this, where this is near the center, this is a velocity. I know you can't really see the labels very well, but this will be the distance. This is the velocity of the stars. And so you expect that the velocities of the stars will decrease as we move further out. However, what we find, and this was found first by Vera Rubin in the late 1960s with Kent Ford, is that in the Andromeda galaxy, she found that stars are actually moving pretty much the same speed, even when you move out to the edge of the disk. That means that stars, if we count up all the mass of the stars in these galaxies and include gas and stuff like that, these stars are moving way too fast. They're moving faster than the escape velocity, where the escape velocity is something that you need to exceed in order to get out of the gravitational potential of something that you're in. For example, when we send out rockets into space from Earth, we need to send them with an escape velocity that will exceed, we need to send them with a velocity that will exceed the escape velocity of the Earth in order to get out of Earth's gravitational pull. These stars are already moving at that speed. So essentially, we should have no galaxies in our sky. This galaxy should have flown apart, unless there's something else that we can't see that's holding it together. Galaxy clusters are another way that we know that dark matter exists. This is something that was first proposed by Fritz Zwicky in the 1930s. He found that galaxy clusters were moving way too fast, like galaxies and clusters were moving way too fast. And so galaxy clusters are these huge gravitationally bound objects of gravitationally bound galaxies of up to hundreds to 1,000 of galaxies in them. And so when he calculated what it should look like, I think he got like a higher amount of dark matter, because at that time we didn't have information about the gas in galaxy clusters. And so what we find today is that actually galaxy clusters have 10 times more there's 10 times more gas mass in galaxies than there is stars. And so I guess if we're looking at just regular matter, the most massive part of those clusters is going to be the gas in them. And even when we sum up all of this stuff, we still find that these galaxies, because now in galaxy clusters, galaxies are moving around in this gravitational potential. They're moving faster than the escape velocity as well. So these galaxy clusters should also not be bound. They should fall apart as well. But another thing that's really important is that there's gas in these galaxies. Gas experiences pressure. And so given the amount of gas mass and stars there are, that potential is not enough to hold the gas down against its pressure. So all the gas in clusters should have essentially spread it out and away from galaxy clusters, but we find that they're still there. So maybe then the one way to explain it is that there's something that we can't see that's holding them together, dark matter. One of the most famous clusters that you see in I guess conversations about dark matter is the bullet cluster. And they call it the smoking gun for dark matter for the following reasons. These are two galaxy clusters that have already passed through each other. So this is your one cluster, and this is your other cluster over here. Now remember, galaxy clusters have far more gas than they do, 10 times the amount of gas, in fact, as there are stars in mass. So with the galaxies, there's so much space in between them that essentially you could assume that they'll just pass by and not interact with each other at all during the collision. In the same way that when Andromeda and the Milky Way collide, stars aren't really going to smash into each other. So there's just too much space in between the stars. And in galaxy clusters, there's too much space in between the galaxies for galaxies to really interact all that much at all. So they'll essentially pass just right through each other. The gas, on the other hand, it drags. So the gas will interact with other gas particles, and that'll cause it to drag in the same way that we experience drag when we fly in the air, in the atmosphere. Gas does the same thing. It's due to gas. So gas is doing the same thing. And in this collision, the gas will drag behind it, which we do see here. The gas in this photo here is pink, and what you see in the blue is actually from gravitational lensing data. But here's where the gas is, and we know that galaxy clusters have 10 times more mass in gas than they do in stars. So if dark matter doesn't exist, then we know exactly where the mass should be, the most massive part, right here. However, what we find is the most massive parts still reside where the stars are, where all the stars are, which is the least massive part of the galaxy. So there must be something, or the galaxy cluster. So there must be something that's holding these together and that's sitting in there that is also collisionless, and that's called dark matter. Gravitational lensing. This is one of my favorites because it's like it's direct proof of Einstein's theory of general relativity that you can see in the sky. where Einstein's theory of general relativity, what Einstein said was that essentially mass bends space-time in the same way that if you were to place like a bowling ball on your mattress, you'd see that it bends your mattress in a sort of bowl-shaped way. Mass does the same thing in space-time, however, on 3 dimensions or in 3 dimensions. And so we can see that this is true because photons in space, so light, photons are particulates of light, they travel straight all the time. They're always traveling straight, no matter what. And so there's a galaxy, a spiral galaxy behind this giant cluster of galaxies here, way behind in the far in the distance, which we would never know if Einstein's theory of general relativity was not correct. If mass does not bend space-time, we'd never know this because it would be blocked in the same way if I was to place, like, say, a coffee cup behind a bush, I won't be able to see it. And so a galaxy behind a cluster would be blocked away by that cluster in front of it. But photons are moving straight in space-time, but they're moving straight along space-time that has been bent, which leads to these beautiful arcs. This is in very close to perfect. It's a case where the spiral galaxy is very close to perfectly central, right behind this galaxy cluster, which leads to this huge arc here. And it's proof of Einstein's theory of general relativity. But another thing that gravitational lensing tells us, these arcs and how they're, or how big they are, tells us how much matter there is in the mass that is bending space-time for it. And gravitational lenses always calculate way more matter than there is due to just the stars and just the gas. So that's something else that shows us how that there must be dark matter. There must be something huge, really massive, that is holding these things together and causing space-time to bend so much. And of course, we have a baby picture of the universe, a literal relic of the Big Bang, the cosmic microwave background. So in this image, which was taken by Planck, the Planck satellite, you see these sort of modeled, it's like a modeled sort of image, which shows you that there are these very slight density fluctuations in the universe. So the universe by far and large is actually pretty homogeneous and pretty even. But there are these very small density fluctuations to 1 part in about 100,000 that cause these modeled, that cause this modeled sort of appearance, where the blue is where density is very high, or well, not very high, higher, and red is where density is lowest. But again, as I said, the difference between that is basically like 100, or one part in 100,000. So it's actually a very small density fluctuation, but it does make a very big difference in how the universe proceeds. So because we had these density fluctuations in the very early universe before it expanded, so when it was still at a very hot and dense state, everything was bouncing off of everything else. We had photons bouncing off of regular matter and preventing regular matter from creating atoms and such. So kind of it's similar to looking at, well, you should never look at the sun, but it's similar to the sun in a sense that in the sun, you have photons bouncing off of everything in that giant ball of plasma. In fact, here's a cool fun fact, is that some photons that travel from the very center of the sun some of them take 100,000 years to get to the surface. And so I think up to even 1 million. And so some of them take very long to get to the surface of the sun and until they roam free. And so in the early universe, you can kind of look at it as something similar to that. And so normal matter, which is the stuff that we're used to, when it's still in its most fundamental pieces, fundamental particulates, kind of tries to, I guess, fall under gravity because it interacts with gravity. And so these little density fluctuations that we saw here, where the denser regions, these would be the denser regions. And so when normal matter tried to fall into these dense regions, photon radiation would push it out, which is why you see this sort of thing happening here. And for the photon radiation is represented by the pink spring. However, when dark matter fell into these same pockets, it doesn't interact with light, so it didn't really care. It just went in and had no problems with the radiation at all. And more of it fell into these pockets, which then formed the seeds for the stars and galaxies that we see today. And it's because it doesn't interact with photons that this was possible. And having that sort of this process in the early universe led to a beautiful, beautiful thing. This is actually art that a friend of mine, Catherine Machen, who we did a project together in last year in June, and essentially she was painting some of the stuff that I worked on, and this is the cosmic web of dark matter. So in these regions you see where the like clusters of galaxies would be, and then here would be filaments. You'd have some gas and some galaxies kind of like scattered across these regions, and then these giant dark areas are actually voids. So these are places where there's no matter, almost no matter at all, and voids can be as 100 million light years across. So they can be very, very large. And this is art, but this comes from a simulation. So on a larger scale, essentially what we were looking at was kind of like a slice of this, let's say, zoomed in. But on a larger scale, you see this across the entire universe. And here again, you see these kind of like voids, where otherwise you see these are like kind of clusters of galaxies, and then filaments along here. They're kind of like create filaments and walls. And this is a simulation, but there's actually data that backs this, and it comes from the Sloan Digital Sky Survey. When you map the sky out, when you map everything out and you zoom out, what you end up finding is that galaxies tend to fall along these clumps and filaments that look on a large scale, when you zoom out as much as you can, look like that cosmic web. And just since we're in a galaxy, our disk kind of blocks some of our view. And so when this starts to rotate, you'll see that there's these sort of two slices, triangular slices, where there's no data, and that's there you go. So, and that's because the disk of our galaxy is blocking it from the view. But otherwise you could see that. And the really beautiful thing about it is that those density fluctuations correspond exactly to the cosmic microwave background. And that's another thing that you require dark matter for this. Otherwise, normal matter wouldn't have had time to do this, and we wouldn't have things like large scale structure, or it would take a lot longer to form. So the question now some of you might be thinking is, what if we just don't understand gravity? What if it's just that? Now, modified gravity is a thing that can explain things like rotation curves. So it does very well at explaining rotation curves. If you modify gravity, you can explain all, like spiral rotation curves very well. You can even explain galaxy clusters and why they still hold together. However, when you look at gravitational lensing and the bullet cluster, these things can't be explained by modified gravity. The cosmic microwave background, absolutely not, and the cosmic web of dark matter. The closest way that, or the closest that modified gravity can get to explaining some of these things is when Einstein's equations are modified. So not the modified Newtonian gravity, but this would be modified Einsteinian gravity, I suppose, where the equations get a lot more complicated than they already are, but it only works if you add extra matter to it anyway. So that defeats the whole purpose. So you end up adding dark matter to this theory while further complicating already complicated equations. And so at this point, modified gravity is not it. So, okay, dark matter probably does exist, but what is it? Some of the things that we now know because of our observations, well, of course, we don't know what it is, but what we do know is that it doesn't interact with light at all and regular matter, because otherwise we would have seen it by now, which means that it's neutral. So it doesn't interact with the electromagnetic force. It does interact with gravity. That's how we see it, is through its interactions with gravity. And another thing that we know is that it would need to be cold. So in this image, or in this sort of, I guess, graphic here, one of the reasons why dark matter also has an easier time falling into these dense pockets is because it's cold. And when we say cold in this context, we don't mean the temperature. We actually mean that it's moving slow compared to the speed of light. And so think about it this way, like if you were to try to contain steam versus containing water, you know, in steam, the particles are moving very fast. And so the faster they move, and then that's where you could get to things like warm dark matter. Warmer is really moving faster. The less the universe starts to look like the one that we see. And so we know that dark matter should be moving slow at the time, at around this time when it starts to create the cosmic web, when it starts to fall into these dense pockets and create the seeds for the stars and the galaxies that we see today. So we know those things. We know that it can interact with light, so it can't be, it's not charged, it is a neutral particle. We know that it interacts with gravity, and we know that it must be cold. So let's break things down and look at particles at the most fundamental level. So here we have the standard model. The standard model is essentially the particle physics version of the periodic table of chemistry. And so here you have all the particles that we understand. The standard model is all the particles that we know of. And so here are your quarks. These are the things like the up and down quarks. Combinations of them are what make up protons and neutrons in atomic nuclei. Leptons are like electrons, and then their heavier counterparts, and neutrinos. And then these are force particles. And then this is the Higgs, the one that gives us mass. So, and of course, I'm featuring my lovely hamsters, which I name after particles, in this model I call teeny symmetry, in which I kind of, because they're teeny and they're so cute. And so my current particles are the ones that we had measured the Schwarzschild radii for, Charmini and Muini. And then we have, of course, gluini, which is the gluon. The gluon is the force particle that mediates the strong force. And so this is the particle that holds together things like up and down quarks and holds protons and neutrons together in atomic nuclei. The photon is what mediates the electromagnetic force, so radiation and things like that. And then here's the weak force. So these are W and Z bosons. These are force particles that are exchanged between particles when you see things like decays. So for example, radioactive decay, when you date rocks to figure out, say, how old the Earth is, that's decay. And that's mediated by the weak force. And so you'll see, this is neutrini. You'll see him kind of placed across all of these because neutrinos oscillate. And so essentially he can be either an electron, muon, or tau neutrino at any point in time. They'll just oscillate and become one or the other. So every single interaction that we have, whether it be a scatter, whether it be something holding things together, whether it be charge, anything like that, has to be mediated by a force. And these are our force particles. Now, this is when you see BSM, beyond standard model. These are particles that we have not found, and that the standard model doesn't predict. So there's the axion, which is Axini, which is a particle that could solve this really interesting problem that we have in the strong force, where we expect to see something that we don't, as well as be a very good dark matter candidate. There's a sterile neutrino, which would be basically the fourth neutrino of these, and it could also be a dark matter candidate. And then there's the graviton, but this is Sterlini, by the way. And then Gravitini standing here for the graviton, which is the part we know gravity exists, but we don't know. What we don't know is whether it's a particle or not. And so the graviton is something we have not yet discovered. Might be because it's a very weak force. It's a very weak force compared to the others. And so we've not yet discovered it. And that is what we call sort of beyond standard model particles. One thing that I want to mention is that neutrinos are known to pass through things. They could pass through, I think, like a light year of lead and not interact with anything. And so neutrinos were at some point thought of as perhaps, something that could be a component of dark matter. The problem is that neutrinos move at so close to the speed of light. They're almost nearly massless. And they move so close to the speed of light that they can't nearly be cold. That would be hot dark matter, which doesn't work. So in the standard paradigm of dark matter, which is called cold dark matter, what's really meant by that is cold collisionless dark matter. So that means that particles that pass by each other won't even see each other. So imagine like taking two billiard balls and throwing them towards each other, and they just pass through each other like ghosts. That's what cold collisionless dark matter would essentially do. It doesn't see any other dark matter particles at all. And remember, any interaction that we have requires a force. It requires a force particle to be exchanged. So maybe there is no force particle through which the dark matter particles interact through. And so that's what really is meant when you hear the term cold dark matter, is really collisionless cold dark matter. And this dark matter is super successful. It's extremely successful at reproducing the whole universe as a whole. So the universe is on large scales. For example, like the giant simulation of the cosmic web that I had showed you, that can be very well reproduced by collisionless cold dark matter. The problem arises when we zoom in on things like these galaxies. So when you go and zoom in, and when I say these galaxies, I really mean the Andromeda galaxy and dwarf galaxies as well. When we make simulations and try to reproduce them, we find that dwarf galaxies are produced far too dense in their central regions. So there's much too much stuff compared to what we observe. Our observations tell us that there's some variation, but generally a lot of dwarf galaxies should not have that much densities in their central regions. And spiral galaxies, because they have so much baryons in them, baryons normal matter, so stars and gas and things like that, because they're so rich with that, they have rotation curves that are actually they vary a lot. And so cold dark matter on its own, like if you use some model of cold dark matter to explain it, it's not really capable of explaining the whole host of these galaxies and what they look like. And so that doesn't mean cold dark matter is wrong, cold collisionless dark matter. It does not mean that it's wrong at all. It could be that, for example, because this happens on, in systems with significant, say, baryonic matter, like if you try to if we simulate galaxy clusters, which are, they have lots of gas in them and whatnot, but galaxy clusters are essentially pretty happy with cold dark matter and can be reproduced just fine. But it's when we zoom in on these guys, which have a lot of baryons in them, like stars and gases forming stars and stuff like that, that we find that simulations are not able to reproduce it. And it might just be that we don't have all the baryonic physics down. But we've started to look beyond that and start to say, well, what if instead dark matter particles do interact, kind of like two billiard balls would actually scatter if we hit another billiard ball with another one. And so when we introduce that scatter, that also would introduce some dark force that we don't understand yet. And if dark matter particles do interact in this way, then galaxies can serve as essentially cosmic particle colliders. So they're huge, giant galaxy and galaxy cluster scale particle colliders that we can use in space to test particles, to test the interactions of these particles. The thing is that when you have different mass galaxies, which we do, so like dwarf galaxies are less massive than spiral sized galaxies. Spiral galaxies are less massive than galaxy clusters. Galaxy clusters are a gravitationally bound cluster of many galaxies. And so if you excuse me. And because the force of gravity is proportional to how much mass you have. So, and that tells you how fast things will move in them. So if you have a gravitational potential that's smaller, you'll have lower velocities. Like in dwarf galaxies, you tend to have like 10 to 100 kilometers per second velocities between these particles. Between essentially stars is what we measure. And so you kind of assume that dark matter particles will follow a similar route. In spiral galaxies, we have, because these are, again, a little bit more massive, so we have speeds of more like hundreds, 200, 300 kilometers per second. And in galaxy clusters, you can have thousands of kilometers per second. For example, in the bullet cluster is an interacting cluster of galaxies. That is a cluster of galaxies where the interactions and that collision took place at like 3,000 kilometers per second. So we have a very different ranges of speeds in each of these types of systems. And so remember, I mentioned that on large scales, cold collisionless dark matter is very successful at explaining galaxy clusters. So large scale galaxy clusters. So galaxy clusters are they're totally happy with cold dark matter, not so much maybe spirals and dwarf galaxies. Well, that tells us then that if self-interacting dark matter is going to work, to alleviate the overdensities in here, while maintaining the success of the galaxy clusters, we'd require that dark matter particle interactions are dependent on velocities, such that when the larger your velocity, the weaker your interactions. And then that would help alleviate the overdensities, for example, that we see in dwarf galaxies, in dwarf galaxy simulations, by introducing these interactions, where these interactions would actually kick out dark matter particles from the center and alleviate that density a little bit. And these would require stronger interaction cross sections than galaxy clusters. Galaxy clusters really want something really small. So, okay, now I've talked about two really different things, or seemingly different things, like dark matter and black holes. So what is the connection here? And the connection is actually the fact that once I turn on these interactions for dark matter, it's the interplay of particle interactions with gravity. So if we have scattering, particle scatters, so like billiard balls scattering off of each other, when we have two particles that scatter, and most of the scattering is going to happen in the center, because the center is where the denser region is. So particles are going to be a lot closer together. When particles scatter, they exchange kinetic energy. So kinetic energy transfers outward from the center. And so that particle that has now imparted its kinetic energy to another particle that it kicked out, that particle that's in the center now loses energy. So what happens when a particle loses kinetic energy is that gravity takes it into effect and pulls it in a little bit closer. And so when that happens, remember that in the solar system, what we saw is that the closer that we get to the sun, the faster the planets move. Same thing here. So once gravity takes into effect and pulls this particle that has just lost some energy closer to it, to the center, it actually starts to move faster. So it just lost energy, but now it's heating up. And as you might be able to tell, is that this is a process that happens as a runaway process. You can't stop it. And so once that continues to happen, you have so much stuff in the center, so much stuff in the central region, that what happens in space-time when you put too much mass into one specific spot, you get a black hole. And so this is what we call gravitational core collapse or gravitothermal core collapse. And so it's because we turn on these interactions, it's because of the self-interactions that we have with this gravitational system, so a gravitationally bound system with particles that are interacting with each other, that we can get something like this, where you have the core collapsing in the end to create a black hole. And these, if this happens early enough in the universe, we can actually end up with black hole seeds that are about 100,000 times the mass of the sun, which solves our problem. If we have a seed that is 100,000 times the mass of the sun early enough, then we can use, accretion, then it can eat up matter and grow in all the ways that we understand, and then explain how we find black holes that are the mass of 1 billion suns at so early in the universe, just 700 million years after the Big Bang. And this is actually one of the pieces of art that that in my collaboration with Catherine Machin. And so here we have these two sort of dark matter black holes, or black holes that were created from dark matter, from this core collapse, and they're now spiraling inward towards each other to merge. So mergers plus accretion, and then we can get to the supermassive black holes that we see in the center of the massive galaxies across the entire universe. And this is not the only possibility. There's actually another possibility of how this stuff how we can create black hole seeds in the early universe, and it's called direct collapse black holes. These are actually really cool. So this is something that can only happen in the early universe, very early, before we had heavy elements at all. So from the Big Bang, we ended up with essentially hydrogen and helium only. Everything heavier and trace amounts of lithium and whatnot, but it's essentially hydrogen and helium. The heavier elements are what were created after stars fused their particles in them and died, and essentially expunged these during their supernova. When they expunged that into their interstellar medium, that feeds it with what we call metals, because astronomers are just very interesting with their naming, and we call anything that's heavier than a helium atom, and it's called a metal. And so this direct collapse black hole mechanism can only happen before any of these heavy elements are created. So we have just hydrogen and some helium as well. And you require like 2 galaxies to be next to each other. One of them that is very gas rich, so it has a lot of gas in it, that is just essentially almost just hydrogen. And next to it, a galaxy that is booming with stars. So and these early universe stars give off this specific type of radiation, and the fact that it's sitting next to this galaxy, it would irradiate it to prevent it from cooling and forming stars. Now, let me explain why that doesn't work in more metal-rich gases. So today, when you have a giant cloud of gas clumping together, these metals, because they're more complicated, like their chemical structure is more complicated, it causes something that we call cooling. So it cools these gas clouds. It cools them down, which causes them to break apart. And this is actually also why we don't see, excuse me. This is actually also why we don't see many extremely massive stars today. Because of this cooling, mechanism breaks these gas clouds down and makes them smaller. It's also why you end up with star clusters, because gas clouds will end up breaking up into these little chunks from the cooling, and then these stars will form together. And that's why you end up with star clusters sort of forming together. And so that cooling isn't going to happen in the early universe because of this galaxy that's sitting next to it, which its stars are irradiating this gas cloud and also preventing molecular hydrogen from forming. So it irradiates it to split that apart and keep it at atomic hydrogen. So you have this giant, huge, massive gas cloud sitting in a galaxy that can't break apart. So eventually, this gas cloud will skip the supernova stage altogether, skip the star formation. There's no star, no supernova, and it just collapses into a never-ending collapse under gravity and creates a black hole. This process would also create a black hole that's about up to 100 times the mass of the sun. So it can also explain how we end up with supermassive black holes by such an early point in the universe, by cosmic dawn. The problem with this is that it has to happen at a specific time. It has to happen very early in the universe, and all of them would have to have been formed then. You can't explain all the supermassive black holes in that way. But I think it's very cool. So one of the things that I'm sure that everyone here is really excited about is the launch of the James Webb Space Telescope. So the James Webb Space Telescope is a telescope that is sitting 1.5 million kilometers or a million miles away from Earth, sitting at this Lagrange point too, where the Lagrange points of Earth are essentially these spots around the Earth where gravity kind of cancels out or balances out due to the gravity of Earth as well as the sun. So due to like a combination of two massive bodies. So Jupiter also has Lagrange points, for example. Any two objects, so any two objects with will have Lagrange points. In fact, even between the Earth and the Moon, there are Lagrange points as well. But we have it sitting at the solar Lagrange point 2. So it's the Lagrange point that faces, so it's going to be kind of like on the opposite side of the Earth and the sun. And the reason why we want it on the opposite side is because that way we can keep Earth, the Moon, and the sun all behind the James Webb Space Telescope. And so by doing that, we prevent any noise from coming in. And the reason why this matters is because this telescope is operating, it's going to be looking at infrared light. So it has to be extremely cold. Any sort of fluctuation in the temperature where which would happen from sunlight, and see this is the shield, so this would shield the mirrors from any of the sunlight or any reflected light off of Earth and the Moon. Any of that could introduce noise into the data, which would kind of, so everything that's warm, even your own body, produces infrared heat. And so any warmth can introduce noise that would introduce infrared data that is false into the data that the telescope would take. And so that wouldn't be good, because we're trying to look at things that are really far away. We're also trying to look at things like exoplanets, for example. Infrared light is really good because it can pierce through a lot of dust clouds. It's also a really good way to look at cosmic dawn, so about a few 100 million years after the Big Bang, because at that point, galaxies that are that far away have expanded away from us to a point where their wavelengths have stretched. So they've stretched beyond the visible wavelength. And we live in a universe that is full of dark energy. And so the universe is expanding faster and faster with the progression of time. Dark energy is kind of like stretching it apart as time progresses. And so the further away things are, the further they shift away from our visible wavelength. And this is why we have never seen that region before. And so we're going to see essentially things like the very first galaxies that ever were formed. We will see the very first stars that ever were formed. So the very first stars are stars that are just made up of hydrogen only and nothing else. We've not found that yet. So we found, those are called population 3 stars. We've not detected any of these yet, but we know that they should be there because these should be the very first stars that formed, and these should be the ones that began to enrich our universe with heavier elements, like anything heavier than helium. And we need that in order to create life, because life here that we have is we require these heavy elements. But we know that these stars should exist somewhere around here. Now, what I'm hoping for is that when we see these galaxies, I'll be able to once data is taken and whatnot, I'll be able to see whether these, like what the galaxy profile looks like. Does it look like these galaxies are getting like denser in the central region? Does it look like there's core collapse occurring? And these are the things that I'm looking for, because if that happens, then that would tell us that indeed self-interacting dark matter and the interaction between particles and the interplay with gravity can lead to creating the seeds for black holes, for supermassive black holes that we see today. It can also tell us whether indeed direct collapse black holes occur. And so I am very much looking forward to the James Webb Space Telescope and what people come up with and what it reveals to us. So we live in a universe with dark energy. So in the very distant future, because dark energy is stretching the universe apart faster and faster with time, matter densities are decreasing. And so eventually it's going to be like the universe is full of nothing but dark energy. Stars will not be able to form because gas will no longer, there will no longer be energy to form any stars. And it will just be extinguished and everything will be cold. And the only things that are actually going to be left over at that time are supermassive black holes. Black holes in general. So stellar mass black holes will evaporate in Hawking radiation in about, I think, like 10 to the 70 years. So that's just a 1 followed by 70 zeros, nothing too big here. While supermassive black holes will evaporate in 10 to 100. So that's a 1 followed by 100 zeros. And so at that time, essentially, we are going to end up, we'll be, if anybody was able to be around for that time, which of course you wouldn't, because not even like matter practically doesn't exist anymore. You can't create anything new. The only thing that will be left behind is supermassive black holes until they evaporate away. And then once that happens, the universe would look like this. But until then, we have a long time to go, more than 10 to 100 years, in fact. So let's enjoy what we see, try to figure out the very many mysteries of the universe, including dark matter and how supermassive black holes formed, and try to uncover all its mysteries, because it's very exciting. And thank you very much. Here's a slide where I dedicate sort of to these little characters who played a part in this talk, and of course the entire universe which played a part in this talk, galaxies and all that and supermassive black holes. And so that's kind of all represented here. And yeah, thank you. I'm happy to take questions now. I'm not sure how that works here.
Yeah, so if you have any questions, regardless of whether or not you're in the YouTube or the Zoom chat, feel free to drop them in. We've got a couple of questions already piling up on the YouTube chat, so I'll just start from there. And then as people formulate their thoughts, which from my experience, I know can sometimes be an arduous process. We'll get to it. So the first question here from YouTube from RP is, could you explain the last steps in logic for why the bullet cluster shows that dark matter must be present? It wasn't clear. Thank you.
Sure. Let me try to go back to that slide, actually. Okay. So in galaxy clusters, we know that this is true for all galaxy clusters. Compared, like the mass in stars is only 10% of the mass in gas. So there's 10 times more mass in gas than there is in stars. And the bullet cluster is a cluster of two gravitationally bound galaxies that have passed through each other. And so these have already passed through each other. This is a larger one and this is a smaller one. And so because the galaxies themselves have so much space in between them, generally you can assume that they're sort of collisionless, if you will. They won't really interact much. But the gas has drag and it will interact very much with the other gas, which would cause it to drag behind. And so this is what we see here. This is actual data. This is X-ray data from this cluster over here. The gas is dragging behind it in this pink region over here, and our smaller cluster here has its gas dragging behind it here. And so when we see, or when we plot the potential to see where the most massive part should be, if there's no dark matter, if it's just the stars and the gas, so just the galaxies and the gas, then this is where most of the mass should be. Because remember, there's 10 times more gas than there is stars, than there is galaxies in galaxy clusters in mass. So there's 10 times more gas in mass in galaxy clusters than there are stars, than there are mass in stars. And so we should see that the potential shows us that this is the most massive region. But when we actually measure it, we still find that the most massive regions, these are potential curves. So like this region here and this region here shows it's very massive. We don't have that kind of happening here. And so there must be something else, because we know that the stars are just 10% of the gas. So there must be something else that's making this more massive and holding the mass where it is, and still giving us the potential where the stars are rather than where the gas is. Does that make sense?
All right, and the next question I've got here is also from YouTube. Benchtech LLC asks, since dark matter interacts gravitationally, does it radiate kinetic energy away via gravitational waves like in spiraling neutron stars do?
So in fact, everything that orbits radiates gravitational waves. Even the Earth does. So yes, but it's not going to be very significant. And the reason for that also is because dark matter is kind of like, it's diffuse. It doesn't form from our measurements. We don't see that it kind of forms into clumps of stuff. Like, so it doesn't like, it sits in a halo around galaxies and around galaxy clusters, but it's kind of like, it's sort of diffuse, and it just kind of throughout the whole thing. You don't have like clumps of it. It doesn't clump together. For example, with anything that you see, like anything that we have, like any object or a hamster, for example, it exists because we have forces that create atoms out of the particles. So the strong force, it helps the up and down quarks come together and create protons and neutrons. And the electromagnetic force gives us the electrons to hold in position around these and create atoms entirely. So, and then these atoms will form molecules, and molecules come together and then form something like my Coke can here, for example. But it seems that dark matter doesn't do that, which means that whatever force, if there are any forces, like a dark force, for example, that does mediate any interactions that it has, it doesn't seem that it's going to be something that would cause it to create sort of denser objects.
And then the next question here from Doug in the Zoom chat. What is the proposed dark matter distribution within a galaxy to account for the angular motion of galaxies that Vera Rubin observed?
So what you're talking about is the Andromeda galaxy. That's the one in particular that she observed. Now, can you just repeat that question for me again? Because I just want to make sure that I'm understanding what the question is.
Yeah, so Doug asks, what is the proposed dark matter distribution within a galaxy to account for the angular motion of galaxies that Vera Rubin observed?
Okay, so the way that dark matter is distributed in galaxies, in fact, that's something that we can figure out by speeds of or what we really call velocity dispersion. So in disk galaxies, we're kind of lucky because we have stars moving in sort of like on a plane and in circular motion around the central region. Whereas if we have dwarf galaxies or elliptical galaxies and galaxy clusters, their orbits are going to be randomized. So they go in whatever which way around that central potential. And so we measure a velocity dispersion. So like it's kind of like the sort of average difference in velocities in a specific part, and then it gives us a velocity dispersion. And so we measure that at different points to be able to produce something called the density profile. So the density profile of a galaxy, for example, like the Andromeda galaxy, would show us where, how the density of matter looks in that galaxy. And of course, you're going to have a lot more density in the center, which is just a result of the fact that, the gravitational potential is deeper in the center because you have more mass there. And so a lot more mass is going to be there, which you'll have a more dense central region. And so it's really dependent on which galaxy we're talking about and what its configuration is and stuff like that. It can be very different. For one of the things, in fact, that I was mentioning was that spiral galaxies can have very different looking sort of rotation curves because of that, because it has a lot of stars in it and a lot of gas and stuff like that. So because of that, it really depends on the galaxy, and we can measure it and then sum up sort of like a mass profile as well. And then that's how we would figure it out.
All right, and this is going to be the last call for questions here. Otherwise, we're going to wind things down. So if you've got a thought or two lingering in your head, feel free to type it in here. Doug just came in with another question, so I'll take this question, and then if we've got two more questions, those will be the last two. Doug asks again, how long do you think it will take for the James Webb to accumulate enough data to address some of the research questions that you have regarding dark matter and black holes? That's a good laugh.
That's a really good question. I don't even think the James Webb is, it's definitely not cooled down to working temperatures yet. So I think it'll take a few years of data, because we're looking at a region that we have never seen before. So we're going to want to get as much data as we can. And then people who actually takes this data, so those will be the observational astronomers. That's not going to be me. But people who actually takes this data will reduce it and kind of give us like things like velocity dispersions and what the velocities look like, maybe a density profile, this kind of stuff from those from that data. And at that point, I would be able to look at it and say, okay, let me see whether this looks like, let me explain exactly what I'm looking for with self-interacting dark matter in galaxies. So initially, we have particles that are interacting in the center. And so, and the largest interactions happen in the center because dark matter is most dense in the center. So you have stuff that's more closer together. And so it has a larger likelihood of interacting with particles there. Initially, what's happening is that it's kicking out particles from the center so that the density decreases. And that's actually what we're observing for the most part in dwarf galaxies now. And that's the problem that we have is it's called the core cusp problem, where in cold dark matter simulations, it simulates dwarf galaxies with a lot of dark matter in the center if we use cold collisionless dark matter. And so we also actually find some dwarf galaxies that are incredibly dense, even more dense than cold dark matter can explain. And this is where the core collapse, the core collapse mechanism that I'm talking about could come into play. Once again, when you have it's kind of like when you play pool and you take you hit your pool stick into like all the balls, you're imparting that kinetic energy from the ball that you are pushing towards them into those other balls, which causes your white ball to kind of stop, maybe move a little bit more, but your kinetic energy has been transferred over to those balls, which spread out, and if you're lucky, you get some in the holes and whatnot, and it's not the 8 ball. And so that's what's happening in there. And because these particles that are in the center are imparting that and kicking out matter at the beginning, eventually, because gravity is taking into effect and kind of pulling these dark matter particles further in, which then start to speed up and heat up, we end up with a galaxy that ends up looking more dense in the center, even more dense than cold collisionless dark matter can explain. And I need to make this clear, self-interacting dark matter is also cold. So it's not like it is cold dark matter, it's just not collisionless. It does experience interactions. So what I would be looking for is to see if we can find at that time, because the James Webb Space Telescope is going to look back as far as 100 million years after the Big Bang, which is really, really, really early. That's where we can see the first galaxies and such. And what I'd be looking for is to see whether we find these small dwarf galaxies that are super dense in the center by this time. And so if we do find that, then we can say that core collapse is happening and could actually be a mechanism for forming supermassive black hole seeds. I know that's a bit more than what you asked, but I thought I should make it sort of clear because that's what I'm looking for. And I think in order to, I guess, be able to make that assertion, we would need a lot of data and a lot of galaxies. So I would say it's going to take a few years.
All right, I haven't seen any other questions, so I'm happy to end things off here. If you're curious in following along with Sophia's work and her work as well in science communication, you can find her on Twitter at AstroPartiGirl. And it's the party in particle, not party as in the thing that I haven't been invited to since before the pandemic. So you can follow her there at AstroPartiGirl on Twitter. You can also find her on Patreon as well if you'd like to support her. And whenever we can, we do like to help others support others, because especially in the world that we have now, that's always a good thing. So I'm happy enough to end my speaking role here. If President Allen wants to come on and say any final words, I'm happy to cede the floor to him. Otherwise, thank you, Sophia, for your time. That was one heck of a talk. Thank you
Thanks so much for having me.
Thank you so much.
Yes, if we were in person, we'd give you a
Alan, you bumped off your sound. Whoops. I have one quick question, Sophia, while you're still there. Can you name all your hamsters to us?
Yes. So it started with it started with Fermi. So Fermi it's spelled F-U-R-M-I, but he is named after Enrico Fermi. That was my very first hamster. But the teeny symmetric particle hamsters began after Fermi. So it's Photini, named after the photon, Neutrini, named after the neutrino, Axini, named after the axion, Sterlini, after the sterile neutrino, Gravitini, after the graviton, Gluini, after the gluon, and my current particles, which are Charmini, who is the charm quark, and Muini, who is the muon.
Do they answer to your names? To their names?
They answer mostly to high-pitched sort of kind of like, you know, like the little cute little talk that you do with your pets. They do answer to that and stuff. So I don't think they answer. I don't really think they answer to their names, but I'll hope that they do. I mean, so one thing that I guess I should say is that the way that I name them is I have them pick their names, and how I do that is by looking at the way that they behave. So Neutrini, for example, when I would reach into his cage, it would seem that he ran through my hand every single time. I could never get him. I'm like, this is totally a neutrino, because neutrinos are passing through us all the time. So I let them pick their names, and I'll assume that they know exactly what their names are.
Thank you.
All right, and with that, we're free from that. So thanks to everyone who once I hear the recording stop notification, I feel a weight lifted off of my shoulders. So thanks again for coming. Much appreciate your time, Sophia. Best of luck with your research.
Thank you so much.
And that concludes my talk. Alan, do you want to say some final words here, and hopefully your mic holds up?
Really, I think we're at the end. Thank you so much, everyone, for attending. Thank you, Sophia, for being our guest at our Paul Sykes Memorial Lecture. It's a delight to have you, and you've given us some challenging things to think about. I hope it's longer between now and the end, when the black holes take over, and it's more time between then and less time from the Big Bang. I think 100 zeros is more than the distance that we can see or that we perceive until the Big Bang, or from the Big Bang.
So we're totally safe. The universe is probably going to outlast that.
In my time, I'm safe, I'm sure. You might be in trouble.
No, I think we'll be totally fine. Black holes will evaporate, and the universe will still be around, and it's gonna happen in such a long time that no intelligent life is gonna be around, not even plants, unfortunately. I know that sounds really grim, but I mean, maybe black holes hold other universes. So for all we know, that would not pose very well for that black hole universe. So because if it's evaporating away, then it would also evaporate. So these are all in really long time spans. So I think we could all be happy and assume that we're safe.
Okay. With that note, good night, everyone.